Some solved problems for Chapter 2. Here we have a physics professor and, walks towards campus. After about 5 minutes, it starts to rain. So you can kind of see, so this is the position as a function of time. So position is a function of time, and around 5 minutes is when it starts to rain. You can kind of see here that, the professor is getting further and further and further away from their house. Starts to rain, turns around, comes back. So what we're looking for is where the velocity is 0. We have points 1, 2, 3, 4, 5. Remember that the slope of the position versus time is going to be equal to the velocity. So let's look at the slope here, the slope right there, the slope right there, the slope right there, and the slope right there. I would say that it's closest at point 4, so part A is going to be 4. For part B, we're looking for when it's constant and positive. You can kind of see, well, that's going to be a negative slope. Here it's going to be a positive slope, positive and positive, and which one of these is the most constant? And I would say that would be 1. You can kind of see the slope is constantly changing. The slope right there is different from those two slopes, kind of the same right here. Constant and negative, but we only have one negative slope, and that's going to be 5. And lastly, we're looking for part D. We're looking for increasing magnitude, so speeding up, and that's going to be point number 2. The slope is getting sharper and sharper and sharper. E, decreasing in magnitude. In that case, we're looking at point number 3, because the slope is going from a large number down to 0. Now, problem number 12. What we are kind of given is we're given the velocity versus time for a race car, and we're looking for the average acceleration during some time intervals, starting with 0 to 10 seconds. So kind of what is the average acceleration in that time interval I've just kind of outlined in red. We know that the basic definition of acceleration is going to be the change in velocity over some change in time. And let's take a look at it for part 1, from 0 to 10 seconds. The velocity goes up to 60 kilometers per hour, and it starts off at 0, so the velocity is changed by 60 kilometers per hour, and all that happened in 10 seconds, so that is the average acceleration. Go ahead and you type all that in, and you're going to end up with 60 kilometers per hour second. Now you're probably thinking to yourself, that is just a weird, messed up unit, and it absolutely is. Probably wouldn't accept that type of unit. So what we need to do is just simply convert that guy into a more conventional meters per second. You all are experts at that right now. You're all experts at that at this point. So that's just simply going to be 16.7 meters per second. And we go ahead and we do that again. So part 1 revisited. So 16.7 minus 0, that's in meters per second now. We've got our 10 seconds down to the bottom. So that's going to be 1.67 meters per second squared. Now for part 2 of that problem, we're looking for 30 seconds to 40 seconds. So kind of this interval right there. In this case right there, it's going to finish at 0. It's going to start off at 16.7 meters per second squared. Time interval is again 10 seconds. So acceleration, simply the change in velocity. And I'm going to get negative 1.67 meters per second squared. This negative sign right here simply says that it was slowing down. The velocity was going from a large number to a small number. Now for part 3, what we're looking for is we're looking for from 10 seconds to 30 seconds. So now we're going to be, just kind of scruple that guy out there. Now we're looking for 10 seconds to 30 seconds. So what is the change in the velocity? Well, that's equal to 0. Change in time, so delta t, all that's going to be equal to the acceleration, divided by 10, so 0 meters per second squared. Take a look now at part 4, IB. Acceleration, simply going to be the change in velocity over the change in time. Well, the velocity starts off at 0, it finishes at 0, and 40 seconds, so it's also going to be 0 meters per second squared. Okay, problem number 21, take a second to read it. It's going to be a constant acceleration problem, and the way to solve these problems is 1, draw a picture, 2, write down everything that you know, and 3, take a look at this table and see which equation applies to your situation. So the baseball leaves the pitcher's hand at 45 meters per second, and it took him 1.5 meters to do that. So kind of draw, the ball starting out, and we've all watched baseball. We know that the ball is going to start off with 0 meters per second of velocity, and very typically we say the initial position is always equal to 0. So cut to the ball 1.5 meters later. Now it's got some velocity that's going to be equal to 45 meters per second, and it took him 1.5 meters to achieve that velocity. And in part A, what we're looking for is the acceleration. So let's come down to this table right here, and actually this one's pretty easy. Time, time, time. So this is the equation I want to use. Now that I've copied it up there, let's go ahead and say, okay, well, I'm looking for the acceleration, but I'm going to just kind of get rid of these guys that are 0 first. So that guy's equal to 0, and that guy's equal to 0, and I'm looking for acceleration, so I want to divide this side by 2x. Do that, I have to divide that side by 2x, and the 2's and the x's are going to cancel out, and I'm going to be left with the acceleration is equal to velocity in the x squared divided by 2 times the distance, so 45 meters per second squared divided by 1.5, and you go ahead and you type that into your calculator, and you're going to come up with 675 meters per second squared. Now for part B, I'm looking for how long it took him to pitch it. So I'll go ahead and say, time is equal to which one. So go ahead and take a look at these equations, and this one right here is going to apply. So I've kind of populated it here. You go ahead and do my zeros again. So initial position is equal to 0, initial velocity is equal to 0, anything multiplied by 0 is equal to 0. And what I can kind of do is say, okay, now I'm solving for time. So I'm going to multiply both sides by 2, divide both sides by acceleration. So put the 2 divided by a, and that's going to cancel out, that's going to cancel out, that's going to cancel out, that's going to cancel out. And then I want to take the square root of both sides to get rid of this square right here. So time is going to be equal to the square root of 2 times the distance divided by the acceleration. Simply say, okay, 2 times 1.5 divided by 675. And you pack that into your calculator, and you're going to come up with a time of 0.0667 seconds. And problem number 28, another constant acceleration problem. Again, the way you solve these is go ahead, you read the problem, draw a picture. It's about a car accelerating on a ramp, and initially we know that the car has no velocity, and let's just say that the initial position is equal to 0. Again, that's very typically what you tend to do. And then the car goes down some ramp, and so it now has some velocity that's going to be equal to 20 meters per second, and it tells us that it took the car 120 meters to do that. For part A, we're looking for what is the acceleration equal to, so come back to this table, hey look, time, 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 and it looks very similar to the previous problem. So I've simply copied it down right here, and let's do the same thing we did before, where we say, okay, well, that was equal to 0, that was equal to 0, and I essentially have the same equation as in the previous thing. We're going to solve for acceleration divided by dividing by 2x. So the acceleration is simply going to be the velocity in the x squared divided by 2 times the distance that it took. So it's going to be 20 squared divided by 2 times 120. And you go ahead, and at the end of the day, the acceleration is going to be 1.67 meters per second squared. Now in part B, we're looking for the time that it took is equal to that. And last time I used this one, let's go ahead and use this guy right here. So Vx is equal to V naught x plus the acceleration multiplied by the time, and that guy is going to be equal to 0. So the time that it took is going to be equal to the velocity divided by the acceleration. So 120 divided by 1.67, and that's going to be equal to, give or take, 12 seconds. Lastly, for part B, we're looking for, well, how far did traffic go while the car was moving down the ramp? And we're going to say, okay, position is equal to rate times time, or velocity times time, if you will. And so we can say The velocity of traffic is told to be 20 meters per second. It took 12 seconds for the car to accelerate, so that's going to simply be 240 meters.